Hello and welcome to the Flow Code Engineering Insights podcast. This is the audio companion to the newsletter. I'm James, the host of this miraculous journey where we will explore the fascinating intersection of Python and engineering. So this is more of an experiment to figure out what subscribers are interested in, and it's essentially a version of the newsletter but in audio form. So in this first episode, you know what? The good thing about podcasts is that it's a little bit less formal, it's a little bit more chilled out, and I can expand on and share some of the ideas that go into the written posts. So whether you're tuning in during a commute or you're at your desk or whatever, at the gym, pumping iron, I'm here to provide some sort of hopefully thought-provoking content that's somewhat informative. So with that being said, let's jump into today's episode, which is going to be a readout version of my post on SciPy in structural and civil engineering, part 3 of 3, structural dynamics, where we will explore structural dynamics with SciPy. And important to note up front, there's a few sections of this post that have code examples. And obviously that would be a disgraceful thing to try and explain in a podcast format. So I'll just highlight that stuff as we work through it. And if you're really interested in the code examples, just go check out the actual written post on my Substack and you can take it away from there. So without further ado, let's jump in. This is the post. Welcome back to the final installment of our exploration into using Python's SciPy library for structural and civil engineering applications. In part 1 and 2, our exploration was anchored in the static realm of structural engineering, using SciPy to solve linear algebra problems and perform optimization tasks. In this final segment, we pivot towards the vibrant world of structural dynamics, delving into the ever-changing and moving aspects of engineering structures. And to quickly recap, SciPy is a Python library that provides modules for scientific computing. It offers tools for optimization, linear algebra, integration, interpolation, and statistics. And it extends the NumPy library, which offers numerical array operations. Moving into structural dynamics, many books are dedicated to the topic of dynamics, so in this post we will just scratch the surface and hopefully ignite some curiosity. Structural dynamics is a complicated topic and has caused me some consternation in my career. That's the understatement of the century. And I'm certain this will continue, and it will for sure. In terms of resources to help wrap your head around the subject and its broad spectrum of applications, my go-to choice has always been Dynamics of Structures by A.K. Chopra. That's a great book. If you're not familiar with it, there's a few different versions. I believe I have the 4th version, and a lot of it is basic principles of dynamics, but it's the most helpful version of any book that I've encountered on the subject. So if anyone has any other suggested resources on the topic, please do let me know. Would appreciate it. Structural dynamics and SciPy. SciPy is well suited for tackling problems in structural dynamics due to the powerful computational modules included, particularly the integrate module, which allows for solving ordinary differential equations that describe the motion of structures under dynamic loads. Meanwhile, SciPy has another module called linalg. That's just the name of the module, and that's for linear algebra operations that are essential when dealing with the mass, damping, and stiffness matrices in dynamic analyses. Both of these capabilities make SciPy a valuable asset for engineers looking to analyze and design structures exposed to dynamic forces. Modeling dynamic systems. Before we can analyze a structure's response to dynamic loads, we need to create a mathematical model of the system. And this often starts with the simplest form, a single degree of freedom system. And a single degree of freedom system can be modeled as a mass attached to a spring and a damper that represents the structure's mass, stiffness, and damping properties, respectively. And in SciPy, we can use arrays and functions to represent these properties and solve the system's motion equations. And to define arrays, in NumPy and SciPy, arrays are grids of uniformly typed values indexed by non-negative integers, facilitating efficient storage, manipulation, and vectorized operations on large data sets, like representing system states in motion equations at each time step. That's a kind of a, if you're not familiar with arrays, that's kind of a complicated definition, but really what they are is how you add a matrix into NumPy or SciPy. So think simply of Excel columns and rows. That's pretty much what you're doing, and you can have a single row, you can have multiple rows, and it allows the calculation of matrices through these different Python libraries. Makes a lot more sense when you see it in action. For more complex structures, a multi-degree of freedom system is required, and each degree of freedom represents an independent mode of motion of the structure. SciPy allows us to expand our models to multiple degree of freedom systems by using larger matrices and more complex functions to describe these interdependent motions. The level of modeling is crucial for analyzing the behavior of real-world structures under dynamic conditions. And this is the key complexity that makes 3D dynamic calculations so challenging. When you're dealing with single degree of freedom systems, it's so much easier to conceptualize the process because you can envision it in a simple diagram. But once you move into multiple degree of freedom systems, things get complicated really quickly, and it can be very challenging to track down the cause and effect of what you're doing in an efficient manner. The direct stiffness method. So the direct stiffness method is a foundational tool in structural analysis. It enables engineers to assess system responses to loads by breaking down complex structures into discrete elements. And its strength lies in transforming the complex interplay of forces and displacements into a manageable set of linear equations, typically resolved using matrix algebra, like the ones that we just spoke about. Dynamic analysis extends the direct stiffness method by incorporating the time-dependent aspect of loads, and it helps solve the motion equations, which are often differential equations, over time steps. This isn't typically a focus of the direct stiffness method, but for certain dynamic problems, especially stuff that considers small variations around an equilibrium, we'll take a look at an example shortly, the stiffness matrix is derived from the direct stiffness method, and it's a crucial component of the mass stiffness damping system that actually characterizes the dynamic behavior of a structure. SciPy offers functions with its linear algebra model that are highly optimized for solving large systems of linear equations and eigenvalue problems and matrix operations, which are core to performing direct stiffness method calculations. And even though SciPy is not specifically tailored for structural analysis, it does provide the numerical and algebraic tools that can be adapted for such purposes. The direct stiffness method, with its explicit focus on structural systems, complements SciPy's capabilities by offering a structural engineering context to the mathematical solutions that SciPy excels at. The direct stiffness method is powerful because it can be applied to a wide range of structure types, and it's scalable for large systems, which make it the foundation for most structural analysis and design software. Taking a first principles approach, the direct stiffness method is used to derive the system's stiffness matrix, which, along with the mass and damping matrices, form the basis for writing the equation of motion. And SciPy's linear algebra module can then be used to solve these equations, which are typically second-order ordinary differential equations in the context of structural dynamics. The next section is related to the equation of motion, and if you want to check that out, you can jump online. But the example that I share is related to a pedestrian footbridge as a single degree of freedom system subject subjected to a rhythmic load due to the collective footsteps of people crossing it in unison. So as people take to the bridge for a early morning jog, the consistent thud of their steps imparts a fluctuating force on the structure, which set it into a dynamic response. And this force, repeated with a regular cadence, like a metronome, provides a consistent push and pull at a frequency that could resonate with the bridge's own natural frequency. So to examine the dynamic response of the bridge to such a force, it can be simplified to have a constant amplitude and frequency. And this type of loading is typical of any events where attendees or participants maintain a synchronized pace, like charity runs, marches, or stadium crowds. I always think about people at concerts or at sporting events that are all jumping up and down at the same time. But it's important to remember that these kinds of harmonic loads could come from a variety of other sources like machine vibration or wind or seismicity or traffic or nearby construction work, that kind of thing. I think in the past I've had to consider nearby blasting operations for excavation in a marine environment. Next section then is a code block, which would be horrific for me to try and read out. So if you're interested in the code to perform this simple check on the dynamic response of that bridge, jump online, check it out. And it's followed by a kind of a explanation of the code, which nobody needs to hear that through a podcast format. But I will finish it off by explaining that the SciPy solver works by stepping through the time span that you've specified for this particular bridge problem. And at each step, it calculates the state of the system using the provided ordinary differential equation function. And then the solver adjusts the step size based on the required accuracy and the behavior of the solution. So it depends, how accurate do you want to be? Do you want to zoom in to the most tiny, minute time step? That will obviously require a little bit more computational effort. But if you think that's overkill, you can zoom out a little bit. You can adjust it to suit your objectives. And it's especially useful for stiff problems or problems that require very high precision over a long time scale. So in summary, the SciPy integrate and solve function is used to numerically simulate the time evolution of the system under the given initial conditions and the imposed external force that produces the dynamic response of the system. And you can expand on this by incorporating much more complex loading or nonlinear behavior of your structure, multiple degree of freedom systems. We can talk about more complex applications for this in the future. So moving on to commercial software and SciPy. Commercial structural analysis software offers a range of computational methods for dynamic analysis, and I do rely on these packages a lot. I am definitely not at the point where I can ditch that stuff and just use Python solely, because it would be ridiculously inefficient for me to try and do that. However, that being said, I am adamant that SciPy offers some distinct advantages, and this kind of applies broadly to Python, other Python libraries, as well as the core Python features. And that is flexibility and customization. SciPy allows for custom analysis and the development of algorithms that are tailored to your specific engineering problems, which can be more adaptable than the often rigid frameworks of commercial packages. Sometimes you just want to look at something very specific or very isolated, and when you build the code yourself through SciPy, you have complete control and understanding over exactly what's going on, and I like that aspect of it. The number two is integration with the Python ecosystem. Being a part of the overall Python ecosystem, SciPy seamlessly integrates with all of the other libraries for data manipulation, visualization, or machine learning, and creates a very powerful toolchain for complex data analyses and engineering computations. Number three, my favorite, open source and community support. SciPy is open source, which means it's freely available without the licensing costs associated with many of the commercial packages. And it's also accessible to engineers and students around the world, which fosters a much more inclusive and global engineering community. This is definitely my favorite aspect. No licensing support headaches. It's free. It's critical. Number 4, transparency and auditability. As I said, it's the open source nature allows for full transparency in the algorithms and numerical methods used. You can see exactly what's going on line by line. You can see what every variable is, how it's defined. There is nothing, it's not a black box because you're writing the code yourself. You're constructing all of the ingredients yourself. Education and knowledge sharing, number 5. SciPy promotes a deeper understanding of the underlying numerical methods, since the users need to implement or modify algorithms themselves, which encourages a more profound learning experience and a more in-depth understanding of the knowledge. And this can be both a blessing and a curse, obviously, especially when you're dealing with complicated calculations. Automation, number 6. Utilizing SciPy within Python scripts enables the automation of recurring tasks or analytical processes and report generation. This level of automation might not be readily achievable in commercial software that primarily operates through a graphical user interface or a GUI, but it's important to note that SciPy itself doesn't come with a GUI. You have the option to develop one if needed. There are a multitude of different types of GUI building libraries for Python that you can build a beautiful front end that you can use to do your calculations. Scalability. SciPy's computational models can be scaled up with relative ease to handle larger data sets or more complex simulations without significant changes to the code base. I think that's a big deal, and it's more of a big deal when you get into larger projects or if you start messing around with machine learning or detailed meshing, finite element stuff that can be more computationally intense. So in conclusion, this series has examined SciPy's potential to supplement your structural engineering process with a focus on real-world application. We've demonstrated that tools like linear algebra, integration, optimization, and interpolation I don't know what I was trying to say there. In conclusion, our series has examined SciPy's potential. Oh my God. Sorry about that, guys. I am not recording this. I'm not re-recording this. I'm at the very end. SciPy empowers engineers to tackle complex dynamic systems with a more autonomous level of efficiency, flexibility, and control. And as we continue to leverage Python's powerful libraries, the scope for creative solutions and process refinement in your engineering workflows continues to broaden. If you're interested in learning more about Python for structural and civil engineering, come and sign up at flowcode.dev. We are building big things. Your feedback and experiences, especially on any unique applications or insights related to this series, are highly valued. Sharing these can foster a richer learning environment for all. Okay, that's it. That's the first Flowcode podcast in audio format. I don't know how this is going to go down. If people are not interested in it, then let's chop it off. Let's cut it off. No more. But if people like this format, please let me know, because that's the only way I will figure out whether or not it's worth continuing to record like this. Okay, be good out there, and I'll talk to you in the next episode.